I'll try, okay? Isn't a fact supposed to be a statement that everyone agrees on? So you would say that a fact is objectively true. Yeah, that's what I mean. Okay, that sounds good. But what about this? We consider it a fact that the sun rises each morning and the earth rotates. But facts like that are not always agreed upon. Look, when we say that the sun rises each morning, we assume that it is the same sun day after day, an idea that might not have been accepted by ancient Egyptians, whose mythology told them that the sun died with every sunset and was reborn with every sunrise. Now let's consider the case of the Earth's rotation. Well, for most of human history, the Earth was assumed to be stationary. Stationary. Stationary at the center of the universe. So, as you can see, our interpretation of facts often are based on beliefs about the world that others might not share. Still, facts are the raw material that scientific models seek to explain, so it's important that scientists agree on the facts. How can we do that? How about this fact has to be verified? I mean, and that's where the testing comes in. So we have to be able to test the model, but we have to be able to test the fact too, right? Now you're on the right track. In the context of science, a fact must therefore be something that anyone can verify for himself or herself, at least in principle. So even though the interpretation may be different, some interpretation of sun is there every morning, and that can be verified. Then a model is proposed to explain the facts, and the model is an explanation of the facts. Right. Once the facts have been observed, a model can be proposed to explain them and not only explain what is obvious but also make predictions that can be tested through further observation or experiments. Let's go back to Ptolemy's model of the universe, which assumes that the Earth was the center of everything. Okay, that was a useful model because it predicted future locations of the Sun, Moon, and planets in the sky. However, although the Ptolemaic model remained in use for nearly 1500 years, eventually it becomes clear that its prediction didn't quite match actual observations, a key reason why the Earth-centered model of the universe finally was discarded. Hmm. So models are discarded when they don't match the observations. Exactly. And new models are proposed to explain the facts in better or more inclusive way. Well, I guess sometimes the model doesn't fail. Okay, how does a model achieve the status theory? Well, I guess sometimes the model doesn't fail, you know. It gets repeated by many experiments and predictions are verified. So when the prediction is verified or repeated, then we start to assume that the model is valid representation in nature. And when that happens with many experiments and a number of different researchers, then the model achieves the status of a scientific theory. 내꽂지. 음, 음, 음. But yes, Jerry. Well, the problem is that the theory get discarded too, don't they? Actually, absolutely, because it isn't really possible to prove that the theory is true beyond all shadows of doubt. And that's good because doubt is a cornerstone of science. Even a well-researched and presented theory should undergo continuous challenges from the scientific community with further observations and experiments. I'm sorry, did we mention the town hypothesis? Does that fit in with a model or a theory? Gradius brought that up. A proposed model is often called a hypothesis. And that just means that the scientist is making an educated guess that the model's prediction will bear up under testing. So a hypothesis is a proposed model, right? But let's put this all together, shall we? Step one is observation, the collection of data. That is observation. Step two is a hypothesis, or a model to explain the facts and to make prediction. Step three is additional observation and experiments. And here's the important part. When the prediction fails, then we recognize that the model is flawed. and we have to revise or discard it. But when the predictions are verified on a consistent basis, then we consider the probability that we have a true representation of nature and we elevate the model to the status of a theory. Step 4 is the theory. Alright, but even then, the theory must undergo step 5, that's further observation, experiments, and challenges. Okay, now for a reality check. For a reality check. In the real world of science, discoveries are rarely made by a process as mechanical as the idealized scientific method outlined in your textbook. The one that we just summarized. For example, anyone recognize the name Johannes Kepler? Sure, didn't he propose the laws of planetary motion? He did in about 1600. But instead of verifying new predictions on the basis of his model, he tested the model against observations that had been made previously. And unlike most scientific discoveries, Kepler's work involved intuition, collaboration with others, moments of sight, insight, and luck. And eventually, as a scientist made a lot of observations too, and verified the planetary positions predicted by his model. Sam, go ahead. So the scientific method in the book. That's not really the way it happens a lot of time. Okay, let's put it in this way. The scientific method is a process that we need to keep in mind as we do the work of scientists. But we should also understand that it's an idealized process for making an objective judgment about whether a proposed model of nature is close to the truth. And we should also keep in mind that in the work of scientists, other factors are also brought to bear on those ideal steps in the process.